Guys, so in this presentation I'm going to be talking about seam carving, which is a method of kind of dynamically cropping an image so as to not crop out important artifacts. So first thing we're going to want to start with is a call to a function called reduce size. So in this function, if the height is greater than 0, we're going to remove that many horizontal seams, and vice versa for the width, and then later we're going to return the final carved image. So the first thing we want to do is, for each seam that we want to remove, we're going to compute the energy map of the current image. Then we're going to compute a cumulative energy map. Then we're going to find the lowest energy seam and then create a new image that skips those seam pixels, and then we're going to repeat that until we've removed the requested number of seams. So we have a current image. First we're going to convert it to grayscale. Then we're going to, for math purposes, convert the pixel values to double. And then we're going to measure how much each pixel changes in the X and Y direction, and then we're going to combine those changes into one number per pixel. A smaller number is going to mean it's a more unimportant, you could say, flat, boring area, and a bigger number means the opposite. So this gives you what's called an energy image, which is the same size as the original, but essentially will have important scores attached to it. So then for each pixel, starting from the top row for vertical seams or the left column for horizontal, we're going to add the pixel's own energy to the smallest of its allowed neighbors from the previous row and column and store this sum in a variable called shadow image. And the result from that is, for every pixel, you know the cheapest total energy to get there from the top or the left. And then we're going to backtrack to find the best seam. So we're going to start at the bottom row or rightmost column, depending on which way we're going, and pick the pixel with the smallest cumulative energy, and then we're going to move one step up or left each time. Every time we're going to choose the neighbor with the least energy. So we're going to record the column for vertical or row for horizontal of each chosen pixel, and the result from that is going to be a list of pixel positions that form the lowest energy seam. After that, we're going to want to remove the seam. For each row, we're going to look at the seam index, which is which pixel to remove, and then copy all pixels before the seam. Then skip the seam pixel, copy all pixels after the seam, and build a new image that is 1 pixel narrower or shorter. And then we're going to continue if more seams need to be removed. And then our last step is to show the result, which goes back to our reduce size function. So here we're going to look at some examples. This is some fruit, and you can see that I messed with the width. So it moved the fruits basically closer together, but it preserved all of them. This house is a house in the mountains. You can see that it made the mountains a little bit more steep looking, but overall it preserved the realistic look of the image. This is a picture of a forest. You can see that the carved image made the trees a little bit skinnier, made the sunshine a little bit less intense, but overall it still looks fairly realistic. This is a railroad, and this kind of made the tracks a little bit more, weird. Overall, still pretty realistic. And then this is some horses that I took a picture of. This was my original picture, and you can see that while it does squish the sky down a lot and it looks cropped, it did preserve like those clouds and all of the artifacts that were in the original image. So this is a more extreme example of when you mess with the parameters too much. These horses look super weird. So for some challenges and what I enjoyed, my biggest challenge was grappling with the complex ideas of the project, but I did really enjoy getting to see the visual results. This method is strong because it's relatively content aware, and it doesn't just crop like regular, but it looks for pixels algorithmically. A weakness is because it's based on local gradients, has no real understanding of what is important, like faces versus background. So you could add face detection to it to make it stronger. And an application for it would be preparing images for web or mobile layouts where aspect ratios matter or change a lot. So that's it. Thank you.